Hi guys, this will be my fourth and last video for Sec 3 IP Physics, and let's start. So the first topic is uh, let me finish this. Uh, Thermal properties, and the subtopics are uh, first the thermodynamics, which I covered in the last video, to heat transfer processes. So in this video, I'll be covering the second part, heat transfer processes. So, okay, alright. There are three types of heat transfer processes. Uh, so there are three. So there are three types of heat transfer processes. The first type is uh, conduction. The second type is convection. The last type is radiation. Okay. So first I'll be talking about conduction. So what is conduction? How is heat transferred through conduction? Alright, conduction is basically uh see where. So conduction is basically vibrations. Okay. So let me use metals to demonstrate a metallic structure to demonstrate. So right, this is kind of, so you learn in chem, this is the structure of a metal. Okay, something like this. Takai. Oh god. Okay. Okay, so this is the structure of a metal, right? Here you have cations, and here it's surrounded by a sea of delocalized electrons. The minus signs are electrons. Alright, um, how conduction is basically um, um, heat transfer of heat energy through vibration. So um, so vibrations. So like let's say this ion in the top left hand corner has more heat energy than others. That means it's vibrating faster. Like that means it's vibrating more. Like heat energy. So it's vibrating more, and so the the reasons metals are able to conduct heat easily is because because of the bonding. The localized electrons can transmit heat energy to other cations very easily. So let's say this starts vibrating, then the electrons transmit the heat energy very easily. So this will start vibrating, So then pretty soon this will start vibrating, this vibrate. Yeah. So basically this is how the energy transmits through a metal. Okay. So on the other hand, let's say you have a giant covalent structure. So it's like let's say diamond. tetrahedral structure. I'm just going to draw here. So assuming this is the structure of diamond or whatever giant molecular structure, other giant molecular structure, whatever. Alright, so let's say here's a carbon atom, and this carbon atom, it vibrates. Okay, the covalent bonds do not transmit heat energy easily, so it's very hard for the heat energy to pass on to like this carbon atom to start vibrating and for whole thing to vibrate. Yeah. Okay. Okay, so that's it for conduction. Oh, okay, got. Okay, right. So next I'll be moving on to convection. So convection, the reason it happens is due mainly to density changes. Okay, so it's like, let's say, mm, uh, mm, so right, it's like, let's say you, mm, so here's a sand or something, you know. So let's say there's a beaker here. Okay, uh, here is so like this. Okay, so and then where is it? Heat is supplied from below, and in the beaker there's a liquid. Can be water or can be some other liquid. Yeah, okay. So like this. So there are two things you need to understand about density to understand convection. So one, so warmer. Let's see. Okay, hotter substances are less dense than colder substances. Oh yeah, and that's it. Convection only applies for liquids and gases, and this also I think. So number one, you need to understand this. Understand colder substances. This is because right. So this shouldn't be too hard to understand because right, like for gases for example, gases for example. So like gases for example, you you have like different gas molecules, right? I just random. Oh, okay, something like this. So let's say in this area you heat the gases up, and such that they become warmer. So this area will start, the gases will move faster, right? And they'll start to expand, right, into the area of others. So because of this, they'll become less dense. Okay, so um, so so with that so it's the same for liquids, and with that, this is what basically why hotter substances are less dense than colder substances. Second thing you need to understand is hotter substances rise rise and okay, I'll put it this way, tend to okay, I'll just say rise. Hotter substances tend to rise and float above, oh, wait, no, dense, okay, that's a substance. Okay, I'll put it this way, less sub less dense substances. Okay, less dense substances tend to rise and float above denser substances. This should be this shouldn't be too hard to understand. I think you should already know this. Like let's say you have oil and water, which is immiscible. You have the oil float on top of water since it's less dense, and yeah. So you need to understand these things, right? So record. So for convection, it's things like you probably heard of like convection currents, right? I'll type it out. Convection currents, right? So convection currents is basically you have so heat is a so let's say in this beaker of water or whatever some liquid, so you supply heat from below. So the area, so the I'll use a different color. So the uh, water in the bottom region, uh, uh, just roughly circle like this, will be hotter than the water in the upper region. So because it's hotter, right? So it will be less dense, and because it's less dense, it will kind of like float to be on top of the colder water. So the hotter water will go up, yeah, like this, and the colder water will come down, and this creates like cycles, like cycles of water coming up and coming down and transmitting energy. So this is so convection currents are also why what like when you heat substances, you heat them from the bottom instead of the top. Because if you heat them from the top, the water there won't be any convection currents, and the water at the bottom would just stay cold. Would just stay cold. Okay. Okay. So the last thing, uh, so the last heat transfer process is radiation. So radiation is um, basically heat transfer through ray EM waves or electromagnetic waves. So let's draw out the whole electromagnetic spectrum. Okay, and this. Okay, yeah, so you have radio waves, microwaves, yeah, infrared, visible light, mm, uh, ultraviolet, uh, X-rays, and gamma rays. So like this. So right, so all these are electromagnetic waves, and they are forms of radiation, which means they contain heat energy. They can transfer heat energy. So for micro, so like let's take microwaves for instance. So right, you have so you find them in microwave ovens like this. And inside you have whatever food you're trying to heat. Okay. So how microwaves heat your food is that from the side they emit these microwaves that are a form of radiation, and this will heat your food. And these microwaves will transmit heat energy to your food and heat it. Yeah. So that's about it. Yeah. So right. So you probably know. So you probably know that you probably know that white surfaces will are the best the best reflectors of heat, and black surfaces are the best absorbers and emitters of heat. So why is this? So first, um, first I'll use an example. Uh, so right. So first, use a simplified version to explain this. Disclaimer. Simplified. So it's basically right. So it's like this. Mm. So so you probably learn in Sec 1, I think, that light is made up of three colors, RGB. Yeah, RGB. So what it means that is that when you so like let's say you have a red surface and a blue surface. So red surfaces they absorb green and blue light and reflect red light. And for blue surfaces, you yeah should absorb red and green light and reflect blue light. Okay, so black is absorb absorb uh, so all three colors and reflect none. White is absorbs none and reflects are red. The three colors. So the thing is, light is a form of electromagnetic radiation. So it's kind of like black surfaces. When they absorb these three colors, what they are doing is absorbing the radiation. And white, when they absorb, um, when they absorb, when they reflect these three colors of light, they're reflecting radiation. Yeah. Okay, right. So now I mentioned um so when these surfaces I light these colors of light are forms of radiation and yeah and you either if black surfaces absorb them, right surfaces reflect them. So why do I say this is a simplified version? So it's because light is actually not just by right it's not just made out of three colors, but but it's actually made up of a spectrum. So light is only made up of three colors when it is coming from things like your computer screen, phone, TV screen, or like digital accessories. But when it comes from like the sun, for example, it's not just three colors, it's a spectrum. So you have uh Roy, so you have all the colors of the rainbow basically. Roy gave birth in Vietnam. You just remember what like Roy gave birth in Vietnam. Yeah, just here's the spectrum. Yeah, so here's the spectrum of colors. So yeah, so the sun emits the color. So the sun, for example, emits light in all these seven colors. So why do um these surfaces why these red surfaces appear red and blue surfaces appear blue? It's because um so instead of just so it's because for the red surface instead of just absorbing green and blue light. So basically what it does is it reflects all the light the red end of the spectrum and it absorbs light at the blue end of the spectrum. So it will also absorb light that is indigo and violet and yeah and reflect red light and perhaps orange light or don't know or maybe yellow light perhaps. For the blue light, right, So it absorbs light at the red end of the spectrum and reflects light at the blue end. So it reflects orange light, yellow light, and what does it so and it probably other than reflecting blue light, it it may reflect the purple light also, depending depending uh, depending on what type of surface it is. So for green surfaces, right, what does it absorbs light at both extreme ends of the spectrum, but it reflects light in the middle. So black absorbs not just RGB, but basically all the colors that you can name off. You can think of orange, yellow, uh, indigo, violet, and yeah. And for white light, it reflects all the colors. Okay, so that's why black surfaces absorb and emit radiation the best, and white reflects radiation the best. Okay, so now I'll be moving on to the last topic of my videos. Waves. Okay, waves. So first I'll be covering the the concepts and terminology, and then after that wave wave refraction in physics, not geog. So first I'm going to explain the what are waves. So waves in physics, there are two types. So transverse waves, and there are longitudinal waves. Okay, so transverse waves look something like so. Transverse waves are like when the wave particles or so they move perpendicular to the direction of wave motion, and so like this. Bad wave diagram, but something. Never mind, I will redraw it. Okay, it looks better. Okay, so this is kind of like how a transverse wave should look like. So what is so how do the particles of a wave move? So they move up and down, right? So let's say like so let's say after a while the particles okay wait, let's mark out. So this I should draw a wave bigger. Wait, so okay, seems better. Okay, so let's just zoom in on this part of the wave. So this is like particles of a wave. So sort of like so, sort of like this. Mm, okay, okay, fine. So this is kind of like dots on a wave. So after a while, so how the waves move? So after a while, let's say this particle moving down. After a while, the particles will look like this. Yeah, so this will be like this portion of the wave after a while. So it's like particle moves down, these particles move down, these all move up, and these all move down. So when you connect them, you get the wave after like after a very short time also. So then after a while, then you could these particles will move further down. Mm, yeah, something like this. Okay, basically something like this. Yeah, after some time. So yeah, so afterwards, so this is kind of like snapshots of the wave in motion at different times. So basically here you see the wave is like this originally. After a while it moves to the right slightly and moves to the right slightly. So here the wave is moving to the right. So okay, so this so this is so this is how so it's like when the particles move up and down they make it look the wave move to the right depending on how the particles move. Okay, so um so the wave particles move sort of like this. And this is like the point of equilibrium. So the wave particles don't actually move to the right themselves, but they move up and down. Okay. Um okay. So right. So so when a wave is moving to the right, it means that so as you can yeah, if a wave is moving to the right, then it means that this part on the upslope, the waves are moving, the particles are moving down, and on the downslope, they are moving up. Okay, and if it's left, it's the other direction. Here, here. Okay. Uh, so, um, so, um, I'll be tell so the wavelength of such a wave would be from here to here. Okay, Okay, so this is the wavelength. The amplitude is the maximum displacement of a wave particle. So here it's this distance. This distance. Okay, so it's like half. So from the topmost position of bottommost position to the point of equilibrium. So this is the equilibrium position. And its the amplitude, as you can see, is also half of the distance between the highest point and the lowest point. Okay, so yeah. Longitudinal waves are waves that the wave particles also move parallel to the direction of motion. So let me use this analogy first. So assume you have uh, let's say 5 people. Uh, yeah, let's say you have 5 people all standing in a line. So the person at the back, he um, he run he runs forward and comes to the guy next to him. So this guy, he cannot stop. He bumps into the person in front of him, and it goes on. Just imagine. Okay, so these are like the particles of a longitudinal wave. Longitudinal wave. So I'll lose lines. So it's like so yeah. So it's basically right. How to say? Waves they so waves you basically yeah. So just imagine it's now okay. So now imagine it's now that scenario, and you instead of the person just moving in front, you have the person moving like this. Okay. Okay. So it's that's kind of like the wave particles. So it moves like this for a longitudinal wave. Instead of moving up and down, it moves left and right. So you have this, and they come closer, become closer. Yeah, something like this, and then get further apart. Yes, they get further apart, and then they get closer again. Yeah, okay, and then yeah. So this is how longitudinal waves look like. So this part, so it's like uh, all these particles, they are moving left, right, and left, and right, and left. So, so, uh, okay, so it's like this. So this part where you where the waves where the particles come closest together is called a compression. And here, where they are the most spaced out, called a rarefaction. Okay, I just imagine. Okay, imagine just now all the people standing in a line. They're moving back and forth and back. Wait, forth, back and forth, and back and forth and back and forth like this. And that's how the particles of a longitudinal wave move, right? So it's like, let's say this is in positions of equilibrium. Like let's say this particle is at the position of equilibrium. So this particle will be a bit further. This one will be a bit further, further until the compression. Then you see the next particle, it starts getting closer to the position of equilibrium, closer, okay, closer, yeah. Then see this is at the equilibrium, then goes towards the left. Then you see the next one, it goes towards the left until the rarefaction. Oh, wait, let me think. Wait, wait. Nothing wrong. So like at the rarefaction, so it starts moving to the left most. So like at the point of rarefaction. So like let's say this is at equilibrium, and next particle will be more to the left until rarefaction. It will start getting closer to the equilibrium position until like let's say this one, it starts going to the right again and it repeats. Okay, so the wavelength is the distance between uh, two compressions or two rarefactions. And the amplitude is the maximum displacement of a wave. So it's like, so it's basically like okay let's say for this particle, it's at the rarefaction. Near the rarefaction, it has the maximum, it is maximally displaced from its equilibrium position. So this is the amplitude. Yeah, okay, nothing else. Okay, okay, so here are the terms, and next I'll be explaining like the equations I should put here. So so um f, yeah, so note v is the velocity, which is the speed of the wave. F is frequency hertz. wavelength is represented by lambda, Greek letter lambda. Is the period. So, sorry, T is the period. Q is the period. What this means is that, like let's say the period is 1/3 second, then that means that, say a source emits the wave one. Let's say the source emits a certain wave, then what it means that is that 1/3 second later, the source will emit the second wave, and 1/3 second after that, it will emit the third wave. So here we have F equals okay, F equals 1 over T. So this F equals 1 over T. So in the case just now, if T was 1 over 3, then F is 1 over 1 over 3, which is 3. So what it means is that 3 waves are emitted per second. Okay. So so you may have heard of the equation V equals F lambda, where lambda is the wavelength. So this is because I'll just use the brush. Okay, so this is because V equals the displacement, the change in displacement. Oh my god, change in displacement over the change in time. So it's like in the period T, a wave would move the length of the wavelength. So it's equal to lambda over T. And since F equals over T, V equals F lambda. Okay, like this. Simple as that. Okay, so here are the equations. Now I'll be moving on to wave refraction in physics. In geog, wave refraction is special to you can go find out yourself. So wave refraction in physics is basically like how it refracts over boundaries and different boundaries and stuff. So first, let me just use the example of okay, so let me just use this example first. So let's say here you have so let's say you have water, and it's water waves going through this tank. So here water waves here. So this is a shallower portion of water, right? So what will happen to the water when it crosses this shallower boundary? The answer is it slows down. It's kind of like because it loses wave energy and stuff, I think. So yeah, so it basically just slows down because it loses wave energy, I think. So anyway, so here we here the velocity decreases, and so thus the wavelength decreases, but the frequency remains the same. Okay, it's because kind of like frequency depends on the source of the wave. So it doesn't. So yeah, so it depends on the source of the wave. So there's no like it will not change. Uh, like in 1 second, in one period the waves will still move one wavelength. Just understand it that way. So to understand why it slows down, you can kind of think of it as like a car hitting a curb, and when the car mounts the curb, it will continue driving on the it continues driving on the curb at the but it will slow down, right? Yeah, and kind of think of it that way. So yeah, that there. So let me explore the different type of refraction. So refraction boundaries. So let's say this is a boundary, and you have wave front coming this way. Okay, coming this way, and yeah. So and when they hit this boundary, they can slow down. They slow down like this. Okay, so like this. So do you uh so right? How do you so if a wave goes this way, what does it mean about the different surfaces? So here you can tell that this portion, the wave is going slower, and so thus the wave, the surface here is shallower, and vice versa. So if they tell you like, oh, here is deeper than here, then yeah, you can say here the waves will be faster than here. So uh, so here right, they still here right, the waves still obey the the obey the law. V equals f lambda. But here, like I explained just now, when they cross the boundary, the frequency doesn't change. Only v and lambda change. So what this means is that v is always remains directly proportional to lambda. So it's like if lambda decreases by 2 times, v also decreases. Like if lambda is multiplied by 2, the v is multiplied by 2. If lambda is divided by 2, v is also divided by 2. So what if they ask you to calculate like the angle of incidence and stuff and refraction? So it's kind of like in light. In light, right? They cross this boundary, it will um it will refract. So but here you have waves instead. So it's like here is the direct okay, let's here is the direction of the waves, and after that here is the new direction of the waves. So like just apply what you learned before in light, in refraction. So I this is R. Yeah, then just use what is it just use NR over NI. Use Snell's law equals sine I over sine R, or or you can move it over. You can just multiply both sides, yeah, and you get this. So you can basically just use this to find the refractive index if the question asks you. And okay, so that's all. Yeah, so that's all for my video, I think, and thank you and bye bye.